There is a question so large that most scientists are genuinely reluctant to ask it out loud. Not because it is unscientific, not because it is unanswerable, and not because it lies beyond the reach of rigorous physical reasoning, but because the answer, if it turns out to be correct, would be the single most destabilizing idea in the entire history of human thought. More destabilizing than the realization that the Earth orbits the Sun rather than the other way around. More destabilizing than Darwin's demonstration that every living thing on this planet shares a common ancestor with every other. More destabilizing even than the confirmation that the entire universe erupted into existence from an incomprehensibly hot and dense state 13.8 billion years ago and has been expanding and cooling ever since. The question is this: is our universe the only one? And the answer, increasingly and with uncomfortable force, appears to be no. This is not fringe speculation. It is not the preserve of science fiction writers or untethered philosophers entertaining themselves with ideas that cannot be pinned down. Some of the most rigorous and respected physicists working anywhere in the world today, recipients of the most prestigious scientific honors, architects of the theories that describe nature at its most fundamental, builders of the instruments that have mapped the large-scale structure of the cosmos with extraordinary precision, believe that the universe we inhabit is just one bubble in an incomprehensibly vast ocean of universes. That beyond the farthest thing we could ever observe, beyond the absolute edge of everything we could ever reach or detect or interact with, there are other universes, perhaps infinitely many of them, each one with its own Big Bang, its own physical laws, its own history, its own particular version of matter and energy, space and time, some of them wildly, unrecognizably different from our own, and some, in the most unsettling version of the idea, disturbingly similar. If this idea is correct, it changes everything we think we know. Our universe, which we instinctively regard as synonymous with reality itself, the container of all that exists and all that ever has existed, becomes a single grain of sand on a beach of infinite extent. The laws of physics that we have spent centuries painstakingly uncovering, and that we are naturally tempted to regard as the definitive and universal rules governing all of reality, may turn out to be no more universal than the weather patterns of one particular afternoon, in one city, on one continent, on one planet. They are what happens to be true here. In other bubbles, in other branches of the quantum wave function, in other solutions to the equations of string theory, different rules apply. Different particles exist. Different forces operate. The history of reality unfolds in directions we cannot imagine from where we stand. But here is what makes the idea more than speculation and more than a philosophical amusement. If the multiverse is real, it resolves, genuinely and elegantly, some of the most persistent and most troubling mysteries in all of cosmology. Why do the fundamental constants of physics have the precise values they have? Why does the universe appear geometrically flat to extraordinary accuracy? Why is the energy density of empty space so incomprehensibly smaller than quantum physics predicts it should be? Why, out of all the possible universes that could have existed, do we find ourselves in one where stars can burn, atoms can form, chemistry can occur, and minds can arise to wonder about any of this? These questions have no satisfying answers in a single universe framework. In a multiverse of sufficient diversity, they dissolve into statistical inevitabilities. They stop being mysteries and start being selection effects. The simple, unavoidable consequence of the fact that we find ourselves here rather than in one of the vast and barren majority of universes where no one finds themselves anywhere. The possibility of other universes cannot be tested in any direct observational sense. It challenges our most fundamental instincts about what science is trying to do and what constitutes a genuine explanation. It sits in a philosophically uncomfortable zone between physics and metaphysics that has troubled thoughtful people on all sides of the argument. And yet it follows with a logical force that is genuinely difficult to escape from the very theories that have proven most successful in describing the structure of our own universe. Understanding how requires us to go back much further than any telescope can see, to the very first moments after the beginning of time, and examine with care what the physics of those moments implies about what lies forever beyond the edge of what we can observe. This is the story of what might be out there, and why, depending on what the answer turns out to be, it may be the most important question that has ever been asked. Stand on the shoreline of any ocean and look outward toward the horizon. Depending on how far above sea level you happen to be standing, you can see roughly 5 kilometers before the sea and sky appear to meet. But nothing actually ends there. The ocean does not stop. The horizon is not a wall or a boundary. It is a geometric artifact, the point at which the curvature of the earth has curved the surface of the water below your line of sight. Everything beyond that line is real and present and continuing. Ships sail there. Storms form there. The water goes on for thousands of kilometers in every direction before it meets land again. You simply cannot see any of it. The universe has a horizon of exactly this kind. It operates by an analogous logic, and it produces an analogous situation. A vast, real, continuing reality that exists beyond what our instruments can reach. In the 13.8 billion years since the Big Bang, light has been traveling outward in every direction from every point in space. The absolute speed limit of the universe is the speed of light, approximately 300,000 kilometers per second. And so the farthest object we could ever observe is whatever source of light has been traveling toward us for the full age of the universe. If space had been static, this would place the edge of the observable universe at a radius of 13.8 billion light-years. But space has been expanding throughout this time, stretching the distances between galaxies, carrying distant regions of the cosmos away from us at rates that, for the most distant objects, exceed the speed of light, not because anything is moving faster than light through space, but because space itself is growing. Accounting for this expansion, the observable universe extends to roughly 46.5 billion light-years in every direction. Everything within that sphere is, in principle, accessible to our telescopes and instruments. Everything beyond it is not. This is not because space ends at that distance. It does not. The universe extends beyond our cosmic horizon, perhaps enormously so, perhaps infinitely so. It continues in exactly the way the ocean continues beyond the visible horizon, in full accordance with the same physical laws, containing real matter undergoing real processes. But light from those regions has not had time to reach us, and in a universe expanding at the rate ours is, much of it never will. The information is simply unavailable to us, and will remain so. This fundamental distinction between the observable universe and whatever lies beyond it is the entry point to the entire multiverse discussion. Because even without invoking any exotic new physics, even without going a single step beyond what we already accept as well-established and thoroughly tested science, the mere fact that the universe extends beyond our horizon implies the existence of regions that have evolved independently of our own, regions separated from us by such colossal distances and by the ever-growing gulf of expanding space that they have never influenced our region and never will. Regions where the same physical laws operate, but where the specific outcomes of every quantum event, the particular initial distribution of every clump of matter and energy, the precise history of every galaxy and star and planet, unfolded completely differently from our own. If those regions are sufficiently remote, and in a universe large enough or infinite enough, they inevitably are, then they qualify as other universes in every practical and meaningful sense. There is no experiment that could distinguish living in a finite universe with a single region from living in one small corner of a vast or infinite cosmos. The other regions are as inaccessible as any other universe. They are, for all observational purposes, separate. And this is just the most conservative and modest version of the idea, the version requiring no new physics whatsoever. When we follow the actual theories that describe the physics of the early universe, the multiverse that emerges is not merely large. It is, in several physically motivated and mathematically precise senses, infinite. On a December night in 1979, a theoretical physicist named Alan Guth was working alone, following a chain of reasoning that had begun weeks earlier with a problem that seemed relatively narrow in scope. He was attempting to explain the absence of magnetic monopoles. Magnetic monopoles are hypothetical particles. They were predicted, in substantial numbers, by grand unified theories, the family of theoretical frameworks that attempt to describe the strong nuclear force, the weak nuclear force, and electromagnetism as different aspects of a single underlying interaction at very high energies. These theories predicted that monopoles, which are magnets with only a single pole, rather than the paired north and south of every real magnet we have ever encountered, should have formed in abundance in the ferociously energetic conditions of the early universe. And yet, despite sustained and sensitive searches, not one had ever been detected. The disparity between prediction and observation was acute. Either the theories were fundamentally wrong, or something had happened in the early universe to eliminate or dilute the monopoles before they could be found. What Guth found that December was a mechanism so elegant and with implications so far-reaching that he wrote the words "spectacular realization" in his notebook. He had identified a process by which the very early universe could have undergone a period of exponential expansion, not the gradual, steady expansion that has characterized the universe throughout the billions of years since, but a ferocious runaway doubling in which the universe doubled in size, then doubled again, then again, approximately 90 times in a period so brief that it would require writing more than 30 zeros after a decimal point to express it in seconds. This inflationary expansion would have diluted any monopoles created before it to densities so low that the probability of finding one within our observable universe would be negligibly small. Their absence is precisely what inflation predicts. But inflation resolved two other major cosmological puzzles simultaneously, and this is what elevated it from an ingenious solution to a specific problem into one of the most important ideas in modern cosmology. The universe, when observed on the very largest scales, is extraordinarily thermally uniform. The temperature of the cosmic microwave background radiation, the afterglow of the universe's first light, varies by less than 1 part in 100,000 in every direction we observe. This uniformity is deeply puzzling because regions of the observable universe that are sufficiently far apart have never been in causal contact. No signal traveling at the speed of light could have passed between them in the age of the universe. How did they reach the same temperature if they could never have exchanged energy? Inflation resolves this by proposing that the entire observable universe expanded from a region small enough to have been in complete thermal equilibrium before inflation began, and that the expansion then flung those equilibrated regions apart to cosmic distances. Similarly, the observable universe appears geometrically flat, neither positively curved like the surface of a sphere, nor negatively curved like a saddle, to a precision so extraordinary that achieving it by chance in a non-inflationary universe would require initial conditions fine-tuned to dozens of decimal places. Inflation smooths away any initial curvature automatically, just as blowing up a balloon smooths the wrinkles on its surface. The observational support for inflation is substantial. The precise statistical pattern of temperature fluctuations in the cosmic microwave background matches inflationary predictions in compelling detail. The distribution of galaxies across hundreds of millions of light-years reflects the signature of quantum fluctuations magnified to cosmic scales during the inflationary era. Inflation is not proven. No physical theory is ever proven in any absolute sense. But it represents by far the most successful framework available for explaining the large-scale structure of our observable universe. And here is the consequence that cannot be avoided. The implication that transforms inflation from a solution to several cosmological problems into the origin of the most profound question in all of physics. In virtually every realistic model of inflation, the mechanism that drives the exponential expansion contains within it an unavoidable feature. Once inflation begins, it is extraordinarily difficult to stop it everywhere at once. Quantum fluctuations in the energy field driving the expansion, the inflaton field, are probabilistic and spatially varying, meaning that while inflation ends in some regions, allowing those regions to settle into the hot, dense state we identify as a Big Bang, in other regions it continues. And because inflating space doubles in size on timescales, many orders of magnitude shorter than any other process, the total volume of still inflating space always grows faster than the rate at which new post-inflationary bubbles form. The inflating background is eternal. An infinite number of bubble universes nucleate within it, each one a separate cosmos with its own Big Bang, its own physical properties, its own subsequent evolution. Our universe is one of those bubbles. This is eternal inflation. It is not a theoretical curiosity or a peripheral consequence of an otherwise tidy theory. It is, given what inflation requires to work, close to inevitable. And it transforms the Big Bang from the beginning of everything into the beginning of merely our local region. One bubble in an infinite and perpetually frothing cosmic sea. Once you accept that eternal inflation produces an effectively infinite number of bubble universes, the next question is whether those bubbles all share the same physical laws, or whether they differ. And this is where one of the most ambitious and most contentious frameworks in theoretical physics, string theory, enters the story. String theory is the leading candidate for a fundamental description of all forces and all particles within a single unified mathematical framework. It replaces the point-like particles of conventional physics with one-dimensional objects, strings, whose different vibrational modes correspond to the different particles and forces we observe. To make the mathematics self-consistent, string theory requires the universe to have 10 or 11 dimensions, most of which are compactified, curled up tightly at scales far below anything we can observe, leaving the 4 familiar dimensions of space and time as the ones we experience. The crucial feature for our purposes is that there is no unique way to compactify these extra dimensions. The extra dimensions can be folded and curved in an enormous number of geometrically distinct configurations, each of which produces a different effective physics at the energy scales we can observe. Different compactifications yield different masses for elementary particles, different strengths for the fundamental forces, different values for the cosmological constant, the energy density of empty space. Each compactification corresponds, in effect, to a different universe with different physical laws, and the numbers of distinct compactifications, each representing a possible physical reality, is estimated to be approximately 10 to the power of 500. Spend a moment with that number. It dwarfs every other large number's physics. The total number of atoms in the entire observable universe is roughly 10 to the 80. The number of quantum states of the observable universe is estimated at around 10 to the 10 to the 120. These numbers are already beyond any meaningful intuition. 10 to the 500 exceeds them so vastly that no analogy adequately captures the difference. It is, for every purpose that matters, infinite. In the context of eternal inflation, each of these compactifications may correspond to a different bubble universe, nucleating from the inflationary background with its own particular version of physical law. The overwhelming majority of these universes will be completely inhospitable to any form of complexity. Some will have cosmological constants so large that space expands too rapidly for matter to accumulate into galaxies. Some will lack stable atoms entirely because their versions of the strong force cannot bind quarks into protons or protons into nuclei. Some will have no distinction between matter and antimatter and will annihilate themselves into pure radiation immediately after formation. In others, the number of large spatial dimensions may be different from our own 3. And in more than 3 large spatial dimensions, gravity obeys an inverse cube law rather than an inverse square law, which means that stable planetary orbits cannot exist, and the solar systems that might otherwise shelter life are impossible. In the vast majority of the 10 to the 500 possible universes, no stars shine, no planets form, no chemistry unfolds, no minds arise. But even if only 1 in 10 to the 500 universes produces conditions hospitable to complexity, the sheer size of the landscape means that the absolute number of hospitable universes is effectively infinite. And we will inevitably find ourselves in one of them, because the barren ones contain no one to take stock of their situation. This is the anthropic principle, and it sits at the explosive center of a debate that has been running for decades and shows no signs of resolution. Whether it represents a genuine explanatory advance or a sophisticated way of avoiding explanation entirely is perhaps the central unresolved dispute in contemporary theoretical physics, and it is worth examining with care. The cosmological constant, the energy density of empty space, sometimes called vacuum energy, has a measured value so small that it qualifies as one of the most astonishing numbers in all of physics. When physicists calculate what value it should have, using the tools of quantum field theory and accounting for all the contributions of virtual particles flickering in and out of existence in the quantum vacuum, they arrive at a number approximately 120 orders of magnitude larger than what observation tells us it actually is. The discrepancy, 10 to the 120, is the single largest unexplained gap between a theoretical prediction and a measured value in the history of science, and no satisfying mechanism for closing it has ever been found. The reason this number matters is not purely aesthetic. If the cosmological constant were even a modest factor larger than its observed value, not 10 to the 120 times larger, but merely 100-fold or 1,000-fold larger, the universe would have expanded so rapidly after the Big Bang that gravity could never have gathered matter into galaxies and stars. The cosmos would be a vast, featureless expanse of thinning gas, growing colder and emptier forever, never assembling the concentrations of matter needed for nuclear fusion, for planetary chemistry, for biology. The measured value of the cosmological constant is small enough to permit a rich and structured universe, and it is difficult to explain why, in the absence of a multiverse. In the 1980s, Steven Weinberg, who had already contributed foundationally to the unification of the electromagnetic and weak forces, applied anthropic reasoning to exactly this problem. In a multiverse where the cosmological constant takes different values in different bubble universes, he argued, we cannot expect to observe just any value. We will observe a value filtered by the requirement that we exist. Values too large will produce barren, rapidly expanding universes containing no observers. Values close to zero, or modestly larger than zero, will produce structured universes where galaxies and stars and observers are possible. From this selection effect, Weinberg predicted that the cosmological constant, when measured, should be non-zero but very small, the smallest value consistent with the formation of galaxies in our past. When the accelerating expansion of the universe was discovered in 1998, the measured value was within the range Weinberg's argument predicted. The prediction preceded the measurement. In the context of a theory that is often accused of making no predictions, this matters. The strong nuclear force presents a similar puzzle. It must be precisely calibrated to allow carbon to synthesize in stellar interiors, If it were a few percent stronger or a few percent weaker, carbon would not form, and no carbon-based chemistry would be possible anywhere in the cosmos. The mass difference between the up quark and the down quark must fall within a narrow range for protons to be lighter than neutrons, enabling the proton surplus that makes hydrogen the dominant element. The ratio between the electromagnetic force and the gravitational force must be extraordinarily large, approximately 10 to the 36, for stars to burn stably over billions of years rather than collapsing catastrophically within seconds. The list extends far, and the pattern is consistent. In each case, a different value of the constant would produce a universe far less hospitable to complexity, and in many cases, completely hostile to it. This apparent fine-tuning has no satisfying explanation within the framework of a single universe, unless one is willing to invoke design or accept it as an unexplained brute fact. In a multiverse of sufficient diversity, the fine-tuning requires no explanation beyond the observation that we are inevitably one of the rare examples where the constants happened to come out right. The anthropic principle, in its most basic form, is simply the observation that any universe we observe must be compatible with our existence as observers within it. This sounds like a tautology, and it is one in the sense that it cannot be false. But it is a tautology with genuine scientific content, because it reminds us that our observations of the universe are subject to a selection effect that standard physics does not automatically account for. We are not sampling universes randomly. We are necessarily sampling from those universes that contain observers like us. In the context of a multiverse, this selection effect does genuine explanatory work. It predicts the order of magnitude of the cosmological constant. It makes the fine-tuning of other constants less mysterious. It explains why we find ourselves in a universe old enough to have produced second- and third-generation stars, necessary for the synthesis of the heavy elements of which rocky planets and living things are made. It explains why we do not find ourselves in a universe a trillion years old, when all stars have burned out and the cosmos is cold and dark. Because such a universe, while physically possible, contains no observers. Critics of anthropic reasoning are numerous, and they raise objections that deserve serious engagement. The most penetrating is the charge that anthropic explanations are unfalsifiable. A theory that explains why the cosmological constant is small by appealing to the fact that we could only observe it if it were small has not really explained anything. It has merely restated the observation in a different vocabulary. If every observation is compatible with the anthropic principle applied to a sufficiently rich multiverse, then the multiverse makes no predictions. And a theory that makes no predictions is not a scientific theory. This objection has real force, and it cannot be simply dismissed. The boundary between a genuine physical explanation and an anthropic tautology is not always obvious, and the risk of using the multiverse as a catch-all for otherwise unexplained facts is one that the physicists most deeply engaged with the idea take seriously. The American physicist Paul Steinhardt, one of the original architects of inflation, has argued that if inflation inevitably leads to eternal inflation and an infinite landscape of possibilities, then inflation itself becomes untestable, because any observation of our universe can be attributed to the specific bubble we happen to inhabit. An untestable inflation is, in his view, worse than no inflation at all. These tensions have not been resolved. They are, in fact, the central unresolved issues in theoretical cosmology today. But the alternative, accepting the fine-tuning of dozens of independent physical constants as pure coincidence, or waiting indefinitely for a unique final theory to explain them all from first principles, is not obviously more satisfying. The multiverse is uncomfortable, but the problems it addresses are also uncomfortable, and they are real. There is a second, completely independent route to a multiverse, one that arises not from the physics of the very large, not from inflation or string theory or the structure of space-time, but from the most precisely verified scientific theory in history, whose implications for the nature of reality have been argued about for nearly a century without resolution. Quantum mechanics works. That much is beyond dispute. From the energy levels of hydrogen atoms to the behavior of transistors in every computer on the planet. From the precision tests of quantum electrodynamics to the detection of gravitational waves by instruments whose sensitivity depends critically on quantum optical effects. The theory produces correct predictions in every domain in which it has been applied. It has never been found to be wrong. And yet the question of what quantum mechanics actually says about the nature of reality, what is actually happening behind the mathematics in the physical world, remains one of the most genuinely open and most genuinely strange questions in all of science. The difficulty is this: before a quantum measurement is made, a particle does not have a definite value for the quantity being measured. An electron approaching a magnetic field does not have a definite spin orientation. A photon approaching a beam splitter does not have a definite path. Instead, the particle exists in a superposition, a precise linear combination of all possible states, each weighted by a complex number called a probability amplitude, whose squared magnitude gives the probability of finding the particle in that state if a measurement is performed. This is not a statement of ignorance. It is not that the electron has a definite spin and we just don't know what it is. The superposition is the full description of the electron's physical state, and the mathematics confirms this with experiments showing interference effects that cannot occur if the particle secretly has a definite value all along. When a measurement is performed and a definite outcome obtained, the theory says the wave function collapses. The superposition instantaneously gives way to a single definite state. But the theory provides no physical mechanism for this collapse. It does not say what constitutes a measurement, or where the boundary lies between quantum systems that obey superposition and classical systems that have definite properties. It simply postulates that collapse occurs, gives a rule for its probabilities, and works. This is the Copenhagen interpretation, and while it is overwhelmingly the most commonly taught version of quantum mechanics, it has never been entirely satisfying to physicists who want to know what is actually happening. In 1957, Hugh Everett, a doctoral student at Princeton, proposed a radical alternative. He asked, what if the wave function never collapses? What if the equations of quantum mechanics, which are smooth and deterministic and contain no term corresponding to collapse, simply evolve forward at all times, including during what we call measurement? The answer he arrived at was that every possible outcome of every quantum measurement occurs, but each in its own branch of the universal wave function, which immediately becomes inaccessible to the others. When an electron is measured and found to be spin up in one branch, an equally real electron is simultaneously measured and found to be spin down in another. Both branches continue to exist. Both are fully real. Reality has not chosen between them. It has divided. The implications of Everett's vision, taken seriously, are almost impossible to absorb in their full scope. Every quantum event that has ever occurred, every photon absorbed or reflected, every nuclear decay, every quantum fluctuation in the plasma of the early universe, has branched the universal wave function into a new set of histories. The number of those branches is not large or very large or astronomically large. It is, in any meaningful sense, infinite. And it has been infinite, or effectively so, since the first quantum events occurred in the Planck-scale chaos of the universe's earliest moments. Each branch is a complete and self-consistent universe. Each one evolves forward in time according to the same physical laws. Each one contains observers, at least every branch that developed in a way broadly similar to ours does, who experience their own branch as the singular and unambiguous reality, with no awareness of the infinitely many alternatives that diverged from their own history at some earlier quantum event. From inside any branch, the universe feels unique. It feels as though measurement genuinely selects one outcome, and the others simply did not happen. The branching is real, but invisible, because the branches cannot interact, cannot communicate, and cannot in any way influence one another once separation has occurred. What does this mean for the concept of probability? In the Everett picture, all outcomes occur with certainty. The question is which branch a given observer finds themselves in. The Born rule, the quantum mechanical formula that gives the probabilities of different outcomes, must, in this framework, be understood as something other than the probability that one outcome occurs and the others do not, because all outcomes occur. Instead, it describes something more subtle: the weighting of different branches, or the fraction of the universal wave function corresponding to each outcome, or the probability that a given observer, before the measurement, will find themselves in a particular branch afterward. Whether this reinterpretation is fully coherent, and whether the Born rule can be derived from Everett's framework rather than being postulated independently, is a question that has generated decades of technical argument and has not been definitively resolved. The many worlds interpretation is not universally accepted. Many physicists regard it as profligate, positing an infinite number of unobservable realities in order to avoid accepting that measurements have single outcomes. Others find it the most economical and self-consistent reading of the quantum formalism, requiring no additional postulates beyond the mathematics itself. The physicist David Deutsch has argued forcefully that the many worlds interpretation is not merely one option among equals, but the only interpretation consistent with the rest of physics as we understand it. Roger Penrose believes that quantum mechanics is incomplete, and that a future theory of quantum gravity will supply the missing physics of collapse. The argument remains genuinely open, which is itself a remarkable fact about a theory that has been in use for a century. For all the philosophical weight the multiverse carries, and for all the legitimate concern about its testability, there exists at least one scenario in which the existence of other universes might leave a directly observable mark on our own sky. And that scenario is being actively searched for right now with real data. In the framework of eternal inflation, our universe is one bubble among an infinite number, each nucleating from the inflating background when the inflatant field tunnels from its high-energy state to a lower one, releasing its energy as the heat of a big bang. The inflating space between bubbles is expanding so ferociously that for the overwhelming majority of bubble pairs, the separation between them grows faster than the speed of light, ensuring they can never interact. But quantum mechanics makes absolute prohibition impossible. In an infinite multiverse producing an infinite number of bubbles, even exponentially rare events occur infinitely many times. Among those rare events is the collision of adjacent bubbles. When two bubble universes collide, the consequences within each bubble are dramatic. The energy of the collision propagates inward as a shock wave, disturbing the matter and energy distribution in a characteristic pattern that reflects the spherical geometry of the collision zone. In our universe, this disturbance would have imprinted itself on the distribution of matter at the time of the collision and would ultimately be visible, if we know what to look for, as a disk-shaped region of anomalous temperature in the cosmic microwave background radiation, with a sharp circular boundary centered on the direction from which the other bubble arrived. Searches for exactly these kinds of signatures have been conducted using data from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, the two most sensitive full-sky CMB instruments ever built. Several features in the CMB have been flagged as potential candidates: anomalously cold circular regions, unexpected temperature gradients, statistical asymmetries that are difficult to explain within the standard cosmological model. None has reached the threshold of statistical confidence required to constitute a genuine detection, but none has been definitively ruled out either. The searches are ongoing, and future CMB missions, more sensitive, with finer angular resolution and more comprehensive polarization measurements, will either narrow these signatures down to confirm detections or constrain the rate of bubble collisions to levels too rare to be expected in our observable sky. The extraordinary prospect is worth sitting with. We may be searching in the data already collected by our instruments for a bruise left on our sky by a universe with different physics, different particles, perhaps different dimensions, an encounter between our cosmos and another that occurred billions of years ago and left a faint but potentially readable mark. Whether such a mark is there or not, the fact that we can look for it, that the prediction is specific enough to generate a search strategy, is itself a significant rebuttal to the charge that the multiverse is entirely beyond the reach of science. It would be dishonest to present the case for the multiverse without giving equal time to the objections, because they are serious, and because anyone who dismisses them without engaging with them carefully has not yet understood the depth of what is at stake. The most fundamental objection is to the principle of falsifiability. Introduced by Karl Popper and refined over decades of philosophy of science, the falsifiability criterion holds that a scientific hypothesis must make predictions that are, in principle, possible to show wrong. This is what separates science from other ways of generating beliefs about the world. A scientific claim sticks its neck out, proposes something specific about the observable universe, and subjects itself to the judgment of experiment. A claim that cannot be subjected to that judgment is not science. And the multiverse, its critics argue, cannot be. No observation within our bubble can confirm or refute the existence of other bubbles. No experiment we can perform can show that the Everett branches are real or that they are not. The theory is constructed by its own logic to be consistent with every conceivable observation. That is not a virtue. It is the signature of a theory that has given up on the scientific method. The proponents of the multiverse have responses to this. They point out that falsifiability, while a useful principle, is not an absolute criterion, and that the history of physics includes many important claims about entities that are not directly observable. The interior of a black hole, the quantum state before measurement, the composition of the primordial plasma before recombination. They argue that the multiverse is not proposed as an independent hypothesis designed to fit a particular set of observations, but as an unavoidable consequence of theories, inflation, and quantum mechanics that have themselves been tested to extraordinary precision, and they point to the cosmological constant prediction as evidence that anthropic reasoning in a multiverse context can generate genuine quantitative results. There is also the measure problem, which is less discussed in popular accounts, but is, technically, among the most serious internal difficulties facing the multiverse program. In an infinite ensemble of universes, how do we calculate probabilities? If every possible value of every physical constant occurs in infinitely many universes, the naive application of probability theory produces absurd results, including the prediction that we should be overwhelmingly likely to find ourselves in a universe with the minimum possible complexity compatible with our existence, rather than one as rich and structured as our own. Various mathematical proposals for assigning a measure over the multiverse have been advanced, each attempting to define what it means for one region of the eternal inflationary background to be more probable than another. None has achieved wide acceptance, and several generate deeply counterintuitive predictions. The so-called Boltzmann brain problem is among the most striking. In certain inflationary measures, the most common observers in an infinite multiverse are not beings that evolved biologically in ancient, structured universes, but rather collections of matter that have fluctuated by chance from the quantum vacuum into the temporary form of a mind, complete with false memories of a history they never lived through. If a theory predicts that most observers are such statistical flukes rather than evolved beings like us, it is in serious tension with our most basic starting assumption, that we are typical observers. Without a satisfactory resolution of the measure problem, multiverse predictions remain qualitative at best, and the claim that the multiverse explains the fine-tuning of our constants cannot be made with quantitative precision. These difficulties are real. They have not been resolved, and any serious engagement with the multiverse has to say so clearly, without softening the point. Not everyone persuaded by the fine-tuning problem accepts the landscape plus anthropic reasoning as the right solution. Lee Smolin, one of the founding contributors to loop quantum gravity and a persistent and eloquent critic of string theory's role in contemporary physics, has proposed an alternative that is more dynamic, more constrained, and in certain respects more genuinely scientific. The starting point is a question about singularities. General relativity predicts that at the center of every black hole, and at the moment of the Big Bang, the density of matter becomes infinite. A singularity, where the theory breaks down and the description of physical reality ceases. Most physicists regard these singularities as signals that general relativity is incomplete, and that a quantum theory of gravity would replace them with something physically meaningful. Smolin suggests that what replaces them, in a quantum gravitational description, is the birth of a new region of space-time on the other side of the extreme compression, a new universe, seeded by the matter that collapsed into the black hole and born with physical constants, similar to, but slightly different from, those of the parent universe. If this is correct, then the multiverse is not a static landscape of all possible constants, sampled anthropically. It is a dynamical system governed by a process analogous to natural selection. Universes that produce many black holes because their physical constants permit the formation of massive stars, which can end their lives collapsing to black holes, produce many offspring. Universes whose constants suppress star formation produce few offspring. Over many generations of universes, the distribution of physical constants drifts toward values that maximize black hole production. And because black hole production requires the existence of massive stars, which in turn requires the same physical conditions that make a universe hospitable to chemistry and life, the universes produced by this selection process will tend to be, statistically, those with life-permitting constants. Crucially, this theory makes specific and potentially testable predictions. It predicts that our universe's physical constants should be close to locally optimal for black hole production. That small changes in most of them should reduce the number of black holes the universe produces, not increase it. Several of these predictions have been investigated and found to be broadly consistent with observation, though the tests are difficult and the results are not conclusive. Whether or not cosmological natural selection is correct, it demonstrates something important: that the multiverse need not be an unfalsifiable metaphysical assertion. In the right formulation, it can be a scientific theory with genuine empirical content. There is a dimension of the multiverse that is rarely addressed in the technical literature, but deserves serious attention, because it bears directly on the most basic question of what the multiverse means for us, for the significance of our own existence, our discoveries, and our history. If the many worlds interpretation is correct, then every quantum event that has ever occurred has branched reality. The number of branches that exist, that are real, that contain observers who experience them as the unique and definitive history, is effectively infinite. Among those branches, there are versions of our own history in which everything went slightly differently, in which some quantum event in the early solar system produced a slightly different distribution of matter, generating a planet with slightly different chemistry, a slightly different history of biological evolution, slightly different sequences of events. The differences compound over billions of years and billions of quantum events. Some branches contain no life. Some contain life, but no minds capable of asking these questions. Some contain minds asking slightly different questions, having lived slightly different lives. Among all of those infinite branches, no two are identical in every detail. The quantum events that shaped the history leading to any particular moment, this moment, the one you are in right now, were resolved in specific ways in this branch, and differently in every other. The specific sequence of every quantum outcome in every particle interaction in the entire history of the universe, unfolding in the exact way that produced this exact moment, exists only here. Every other branch diverged at some point, even if only imperceptibly. In an infinite multiverse, there may be branches arbitrarily similar to ours, but there are no exact copies. This means something that is not often stated directly. Even if the multiverse is real, even if our universe is one grain of sand in an infinite beach, the specific history of our grain is irreplaceable. The particular sequence of stellar births that produced our sun, the specific orbital dynamics that gave our planet its liquid water and plate tectonics, the exact evolutionary contingencies that produced the species that builds telescopes and asks questions about infinity. All of that happened once. It is happening once. The other branches have their own histories, equally real and equally singular. Ours is no less so for sharing an infinite context with theirs. This question, can we ever know whether the multiverse is real, deserves the most honest answer that the current state of physics allows. In the strict sense of direct and unambiguous observational confirmation, probably not. The bubble universes of eternal inflation are separated from us by expanding space that grows faster than any signal can cross. The branches of the many worlds interpretation are inaccessible by the very mechanism of their formation, which permanently entangles each branch with its own version of the macroscopic world. The other vacua of the string landscape, if they correspond to real regions of an eternally inflating background, lie beyond any conceivable observational reach, but cannot be directly observed and cannot be scientifically addressed, are not the same thing, and the history of physics is full of entities that were inferred before they were observed, or that have never been observed directly, but whose existence is compelled by theory and confirmed indirectly. We infer the existence of black holes from the behavior of matter and light near them, not by crossing their event horizons. We confirm the existence of the neutrino from the conservation of energy in nuclear decays, long before detecting it directly. We accept the existence of quarks, which are permanently confined inside hadrons and can never be isolated, because the theory that describes them makes predictions confirmed in extraordinary detail by experiment. Indirect inference, built on well-tested theory and confirmed by observation of consequences, is not a lesser form of knowledge. It is often the only form available. The multiverse can be approached the same way. We can ask whether the theories implying it are well-tested. We can search for indirect signatures such as bubble collision imprints in the CMB. We can ask whether cosmological natural selection's predictions about our universe's constants are confirmed by detailed study. And we can wait for the possibility that future theoretical progress will reveal ways of probing multiverse predictions that we have not yet imagined. The history of physics is full of measurements that would have seemed impossibly subtle to earlier generations. The bending of starlight by the sun, confirmed in 1919. Gravitational waves from colliding black holes a billion light-years away, detected in 2015. The Higgs boson, predicted in 1964 and found in 2012. The universe has repeatedly proven more accessible to human ingenuity than it initially appeared. Whether the multiverse is ultimately confirmed, ruled out, or remains forever ambiguous, the questions it forces us to confront: what counts as an explanation? How probability operates in an infinite ensemble? What it would mean for physical law to be contingent rather than necessary, are among the deepest and most important questions that science has ever encountered. Progress on them will reshape not just cosmology, but our understanding of what science itself is capable of. When the full scope of the multiverse is laid out, the infinite landscape of string theory vacua, the eternal cascade of inflating bubbles, the uncountable branches of the quantum wave function, there is a natural and understandable temptation to feel that it diminishes everything. If our universe is one among infinitely many, if the laws governing our reality are simply one random draw from an incomprehensible lottery, if the entire history of our cosmos, every galaxy, every star, every life, every thought, is a negligible local episode in a story of infinite extent, then what significance can any of it have? Why does it matter what we discover, or build, or understand? What meaning can attach to a universe that is, by any cosmic accounting, indistinguishable from nothing? This temptation should be resisted, and not merely on the grounds of sentiment, though sentiment has its place. The fact that the cosmos may be infinite does not make our region of it less real. The fact that other universes may exist as bubble nucleations in eternal inflation, as branches of the universal quantum wave function, as other solutions to the equations of string theory, does not make this universe less extraordinary. We live in a universe that, through the specific values of its physical constants, and through the specific quantum outcomes of its entire history, permitted matter to form, stars to shine, planets to coalesce, chemistry to unfold into biology, and minds to emerge that are capable of tracing the logic of the cosmos back toward its origin. Whatever the ultimate explanation for these facts, design, selection, necessity, or the sheer productivity of infinity, they are the irreducible facts of our situation, and they are genuinely astonishing. The multiverse does not end the project of understanding. It deepens it immeasurably. It raises questions that cut deeper than any physics has asked before. What is the relationship between mathematical existence and physical existence? What does it mean to explain something in terms of an ensemble of unobservable realities? How should probability be understood when every possible history occurs infinitely many times? These questions sit at the intersection of physics, mathematics, and philosophy of science, and no single discipline has the tools to answer them alone. The progress that does come will require not just more sensitive instruments or more powerful accelerators, but more careful and more rigorous thinking about the foundations of what we are doing when we do science at all. We are, perhaps, The first generation of minds to seriously and systematically grapple with the possibility that the universe, the largest thing we have ever had a word for, the ultimate context of everything we have ever known, is itself a local region of something so vast that vast fails completely as a description. That thought carries genuine vertigo. But alongside the vertigo, there is something that does not diminish with the scale of what we have discovered. Because a species that evolved on a small and ordinary planet, under an unremarkable star, in one galaxy among hundreds of billions in one observable universe among potentially infinitely many, has nonetheless found its way, through patience, ingenuity, mathematics, and the willingness to follow an argument wherever it leads, to the edge of everything it can possibly see. And there, at that edge, it has looked out into the dark and asked what lies beyond. 13.8 billion years ago, our universe began. Everything we have ever measured, imagined, built, or loved unfolded within it. But if eternal inflation is real, if the mathematics of quantum fields is telling the truth, if string theory's landscape of possible realities corresponds to actual physical regions, then ours was not the only beginning. An effectively infinite number of other universes began as well, each with its own laws, each writing its own story, each forever beyond our reach. They are out there. And the fact that we can reason our way to their existence, that the same minds shaped by billions of years of biological evolution to find food and avoid danger on an African savanna have extended their reach, through mathematics and logic and observation, to the outer boundary of all possible knowledge, is perhaps the most extraordinary thing that has happened anywhere in any of them.